Okay, so this is question number 7 of the nuclear physics homework booklet. And in question number 7, we're looking at a radioactivity experiment to start off with. And in this experiment, background radiation has been taken into account when taking readings in a laboratory. We're told that one source of background radiation is from rocks on which the lab is built, and we're simply asked to give two other sources. So it can't be obviously rocks, it needs to be two other sources of background radiation. There's lots of sources. I just went for cosmic rays and radon gas, both of which are sources of background radiation. Really, you need two sources of background radiation for your 1 mark. In part B, we're told that a gamma ray detector has got a cross-sectional area of 1.5 times 10 to the minus 3 square meters when it's facing the source, and it's placed 0.18 meters from the source. When it does that, a corrected count rate of 0.62 counts per second is recorded. We're then kind of given a hint, because we're then told that we need to assume that the source of gamma radiation emits these gamma rays uniformly in every direction. So it's not, the gamma rays are not just coming towards our detector, they're going every way that they possibly can do. So they can go up, down, left, right towards us. So actually they form at a certain distance away from the source. There will be a sphere around them at that particular distance where all of these particles are travelling through this sphere. So we're asked to show that the ratio of the number of gamma photons incident on the detector, in other words, the number of photons that actually the detector could detect, divided by the total number of photons is given by this thing here. Now this is a fairly, in some respects, is a fairly complicated question, because what it's really asking is it's basically saying, right, okay, the photons are given out in every single direction they possibly could do, but the detector is only going to actually detect potentially a very small portion of these. So how are we going to work out the proportion of these total number of photons that are given out just for this small area? Well, if we know the total area of the sphere, then we could actually then work out what proportion the area of the detector is of the sphere, which is basically what we need to do. So if we can work out, if we know the area of the detector, which we do, it's given here in this question. If we know the total area altogether, which is the area of our sphere, if we work out the ratio of the area of the detector to the area of the sphere, that'll basically tell us the ratio of the number of photons that are given on the detector to the number of photons produced altogether, because they go out in every single direction. Now the area of a sphere is given by this equation, so it's 4 pi r, actually that's wrong, it should be 4 pi r squared, which is actually correct down here, so sorry, ignore that. And the radius, it will be the distance that the detector is away from this particular source. So the radius is 0.18 meters. So the ratio we've got is the area of the detector, so 1.5 times 10 to the minus 3 square meters, divided by the area of the sphere, so 4 pi and then the radius squared. And if we do that, we get 0.0037, which is roughly 4 times 10 to the minus 3. So for your 2 marks, you basically get 1 mark for using the area of the sphere correctly, and then 1 mark for showing that the ratio is about 0.0037. In part 2, we're then told that the gamma ray detector only detects 1 in 400 of the photons that actually hit the detector. And we're asked to calculate the activity of the actual source and give a unit. So we know that activity is defined as basically the number of decays per second. The corrected count rate altogether is given by this. So this is the activity that the detector detects. It's back up in the question up here. So the actual detector detects 0.62 counts per second, but it's only detecting a small fraction of it. So we need the whole number of particles that are given out. So if we divide the 0.62 by the fraction, it'll basically give us the number of particles in total that a detector would detect, and that gives us 167.56, etc. But the detector only registers 1 in 400 photons. So this is only kind of 1 in 400 of what it should detect. So if we multiply this number by 400, that'll tell us altogether the total number of photons that are given out. And if we do that, we get 6.7 times 10 to the 4. And because we're working out an activity, the unit of activity is the becquerel. So your 3 marks: 1 mark for your unit, 1 mark for the correct answer, and 1 mark basically for working out this part here, so working out the corrected count rate altogether. In part C, we're then asked to calculate the corrected count rate when we move the detector a further 0.1 meters away from the source. Well, this is a gamma source, and so as soon as we see the fact that we're moving a detector away, the very first thing we should think about is this. Okay, we should go, right, gamma, it's gamma radiation, that follows the inverse square law. Now, the inverse square law basically tells me that the intensity or the count rate multiplied by the distance squared the detector is from the source at one point is equal to the count rate at a second point times by the distance squared at that second point. So I can take this equation and put my numbers in. So if I think about where it was to start with, where the detector was to start with, well, at that point the count rate was 0.62 and the distance was 0.18 meters. So I put that into the first part of this equation here. So that's the count rate, that's the distance squared. That's equal to the one. I then move my detector. So this is then equal to the count rate where I've moved it to multiplied by the distance. And the distance is now 0.28 meters because it was 0.18, but it's been moved a further 0.1 meters. So it's now 0.28 meters. So I simply rearrange this equation and put these numbers in my calculator. Gives me 0.26. So my 3 marks, I get 1 mark basically for attempting to use this inverse square law. I get 1 mark for putting my numbers in correctly, and I get 1 mark for the correct answer. And so that was question number 7 of the nuclear physics homework booklet.